Alright, hello and welcome back. So in today's lesson we're going to learn a very cool topic, which is volumes. So up till now in your math education, you probably are familiar with taking volumes of like cubes, rectangular prisms, pyramids, spheres, things like that. But as we know, not all solids are those solids that we already know. So how can we find volumes of more complicated objects? That's what we're going to learn today. We're going to learn how to find volumes of these very, very intricate or a little bit different shapes than we're used to. Now, just as a warning before we get into this section will require quite a bit of drawing and sketching things out. I'm not very good at art, so I'll try my best to make it look good, but you'll just have to bear with me. And a lot of this comes down to visualization, so I highly encourage you to draw it out as we go along too. It'll all make sense in just a moment, but hopefully what I've done will help you visualize it. All right, let's get into it. I hope you like my hat. Let's do it. So, volumes by cross-section is what we're going to look at. So, yeah, let's read the little blurb. It says like this section can be quite difficult to conceptualize, which is what my warning is. But the idea of what we're going to do is we're going to use integrals to evaluate the volume of these 3D figures. But these 3D figures are constrained in that they're bounded by two curves, and their cross-section is a familiar geometric shape. Okay, so what does that mean? This is the general form of the equation that we'll be using. The integral from a to b of a of x dx. So you'll notice that x is the variable within this formula, so we're going to be looking at how things change along the x-axis. So in the figure below, we have a and b as sort of the bounds of our 3D figure, where they're chopped off. So intuitively, if we were to take a definite integral, it makes sense to start at a and go to b, or maybe from b to a, something like that, right? Because those are where it's bounded. But that doesn't mean too much. Anyways, what are we integrating on? We're integrating on a of x. In this figure, a of x is this cross-sectional area. So this brown part of the figure is a cross-section. We're slicing down on our 3D figure, and a of x is going to be the area of the shape that I just highlighted in red there, the area of that cross-section. And in this case, it kind of looks like a square or a rectangle, right? So we know how to find the area of a square or a rectangle. That should be pretty easy to do. But notice how a of x is a function of x. It's not always going to be the case that it's going to be a constant. So what do I mean by that? For example, let's assume that this shape here is a square. Why not? So then the a of x is going to be the side length squared. Well, how do we get the side length? In this case, it's going to be the distance between this line in the back and this line in the front. The distance between those two lines is this red line, which is the side length. So the side length squared will give us a of x. And it's a function because this side length is going to change depending where we are. If we take a different cross-section over here, we can see that this bottom side length is a little bit longer than here. And similarly, if we go further down to the left, we're going to have a smaller side length. So it's a function, it's changing as we go along. And what's interesting here is we're multiplying a of x by dx. Dx is going to be basically this delta x, a very, very tiny thickness. So if we're multiplying an area by a thickness, and let's just assume that this area here is like of a square or of a rectangle, that's the same thing as finding the volume, but what we're doing is we're finding the volume of a very, very thin slice of it. And an integral is a sum, so we're taking the sum of the volumes of all of these thin slices from A to B. And that's how we're obtaining the volume of this figure. Hopefully that made sense, but very briefly, let me sort of do a tangent and explain with a simpler shape what's going on. So this is a cylinder, right? And the volume of a cylinder is pi times r squared h, right? That's what we've learned. We can think of finding the volume of the cylinder in a similar way, in that we take a cross-section which has a very small thickness. In this case, the cross-section is a circle, so the area of that cross-section is pi r squared, and then we're doing a very little thickness. So let's just multiply that by like a very small h, and then we're summing them all up, all of these little disks up until we reach the entire volume of the cylinder. The way I like to think about it is we're basically taking like circular pieces of paper and just lining them all up until we get the cylinder. And the same thing here. We're taking these square pieces of paper and building the shape, and the square might change in size. All right, that was a really long explanation, but it's critical to understand what's going on so we can actually solve the problems. Because the problems now will just be a lot of just going off of what we just did and praying that we can visualize it. Let's do it. But first, let's look at the formula. So if the cross sections of area A of x are taken perpendicular to the x-axis, then the volume is given by this equation here. So if we go back up here, these cross sections were taken perpendicular to the x-axis. We were slicing down on the x-axis, so we used this equation here. If the cross sections are taken perpendicular to the y-axis, then we have this formula, which is very similar to the first one, except now note that the integrand is in terms of y, so we might have to do a change of variables. We'll do a problem just to be familiar with it. Okay, and then usually a of x and a of y are determined by simple geometric formulae. So we saw like up here, we assumed that a of x was a square, or it kind of looks like a rectangle too. Here, a of x would be a circle. So those should be very easy to figure out, which will be nice because then we can figure out the integrand really easily. And just for your reference, for square cross sections, a of x would be s squared. For semicircle cross sections, 1/2 pi r squared. Circle cross sections, pi r squared. Equilateral triangle cross sections is this fun formula here that gives you the area of an equilateral triangle. These are just some common shapes that I've seen in problems like these, so I just noted them down for you to be familiar with. If you don't know this formula, highly recommend you memorize it. It's super helpful. Let's do some problems to figure out if we understand what's going on. So, ignore the black box for now, it'll come in useful in just a moment. Find the volume of the solid whose base is the region bounded by the following two lines and x equals 0, using square cross sections perpendicular to the x-axis. That's a lot to take in, and some people might be able to just go into solving it, but for me, I really like to draw a diagram because I need to be able to see what's going on. So if you're a visual learner like me, feel free to draw it along with me, and it'll be helpful for me when we actually solve the problem. First thing I like to do is sketch what the base looks like. We know that the base is bounded by these two lines and x equals 0. So let's just graph these on an xy plane, and then we can add in the third axis later, right? And I say xy because we'll treat these as like y equals 1 minus x over 2, and y equals negative 1 plus x over 2. So let's do that. Let's zoom in here. That'll be my y-axis. This will be my x-axis. And first we have y equals, oh man, I already forget, 1 minus x over 2. So you can find your like points of intersection. Actually, I think we will do that. We know that the y-intercept of the line is at y equals 1. And then the slope is negative 1/2. So you go down 1 and over to the right 2. So it's actually going to be something like this, right? Where x equals 2 there. The other equation is y equals negative 1 plus x over 2. So here the x-intercept is negative 1, and the slope is 1/2, so you rise 1 and go over 2, and that'll take us something like this. The region is bounded between those lines, so, and also x equals 0, which would be this vertical line here. So the base is going to be this triangular region here, right? So that's what the base is going to look like, this triangle with endpoints at 1, negative 1, and 2. All right, now let's try to sketch the 3D figure of it. So let's zoom in here. So what we're going to do is, this will be our y-axis. Our x-axis will come like this, and our z-axis will be like that, maybe a little bit taller. So it's a weird view of our 3D coordinate system. Usually we do something like this, but I've cut off some parts of it because I know that the base extends only to the right of the y-axis. So everything over here on the xy plane doesn't really matter to us. If that doesn't make sense, let's draw it out and you'll see what's going on. So first let's start by drawing out the base. So again, we'll draw the two lines that we drew here, this one and this one, except now we're doing it in this skewed view. So like this is the xy plane, sort of ignore the xz axis. So the first line went something like this, where this was positive 1 and this was positive 2. And the second line went something like this, where this is negative 1. All right, so we can hopefully see the resemblance. This line is the same thing as that, and this line is the same as that. Cool. And sure, if you want, we can highlight in the base, but I'm actually not going to do that because it'll make the diagram messy. So we've drawn the base. Now we have to make it three-dimensional using square cross-sections perpendicular to the x-axis. Okay. So we've drawn our base. Now we have to consider when we slice down on this figure, we need to be getting square cross-sections. So let's just take some location within this figure along the edge here. Somewhere there, okay? And we're imagining a cross-section that goes perpendicular to this x-axis. So what we're going to do is let's draw a line through here which is kind of perpendicular to the x-axis. And I'll kind of like extend it upwards. And this like dotted red rhombus is, you can imagine that's like the plane which is slicing our figure. But we don't have the full figure yet, we're going to draw it. Let me just erase some of what I've just drawn, but that was just for the sake of viewing it. Okay, so really let's just look at the part that goes within our figure here. So this red dotted line, that's within our figure, and we want a square cross-section. So if we look back up here, it's very similar to this drawing up here where we have this brown part being the cross-section, except in my drawing it's red, and we want to draw this square upwards. So the red dotted line, which we'll go back to in just a moment, is basically this line, where it's sandwiched in between two lines of our base, right? You can, like, this is the first line and this is the second line, and that red dotted line is sandwiched in between. That's going to be our side length. So using the side length, we want to build a square upwards. And from there, we can hopefully construct these other lines. Hopefully that makes sense. So what I mean, using this, we know this is going to be like our side length. Let's try to draw a square in a 3D perspective. That would be our cross section. Something like that. Hopefully that looks good. It doesn't look great, but it looks okay. But you can imagine that the plane that contains this red square is going to be what we're cross-sectioning. It's perpendicular to the x-axis, and that red square will be our square cross-section that we need. It's perfect. So we have something, but we don't have everything just yet. We kind of want to... Let's maybe do another one, and I like to do the extreme point, just so I can get an understanding of what's going on. So let's go all the way to the left and draw another red dotted line. And you can extend it, but remember, we're looking in between inside of our figure, so it might be hard to see, but the red line is on top of this. And we're going to do the same thing. We're going to draw a square based off of that red line. So we're going to extend it upwards in a 3D perspective. Something like this. And then go over. Oh, this is really bad. And then come down. And that's as far left as we have to go because we're also bounded by the line x equals 0. So that's why the left part of the diagram doesn't really matter, right? Everything over here, because we're bounded by x equals 0. So now we can start to see what the figure looks like, right? We've drawn two cross sections, but you can imagine a bunch of other squares in between them. And eventually we can kind of draw the line that they'll follow. So it'll look something like this. Right? It might be hard to see, but hopefully it's starting to make sense what's going on here. Hopefully you're starting to see this figure. Alright, it's kind of like a pyramid. Not really though, but... And you can see that red square, this red square, that would be a valid cross-section of our figure. Right? If we were to slice down on it at this point here and here, this is going to be our cross-section. And all throughout our figure, we have these square cross-sections. So this is what our figure looks like. The picture is a little bit weird, but what I'll do is I'm actually going to erase whatever I've drawn on the right-hand side. Because first, let me get rid of this black box. I've drawn it already here, and you can see that it's basically exactly the same as what we did, where the blue triangle at the bottom is our base, right? This is our line f of x, this is our line g of x, this is x equals 0, the base is bounded within that, and then we did the same thing, where you draw these squares, and then the rest of the lines are determined based off of that. And without all of the axes and such, it looks something like this. That's the best kind of drawing I could do of it. Hopefully that helps. Okay, so up till now, we've just drawn the figure. We have not done any of the math yet, but the math is going to come a lot easier now. So, first we need to figure out which equation to use. Our cross sections are perpendicular to the x-axis. So that means we're going to use the formula volume is equal to the integral from a to b of a of x times dx. And what I'm going to do quickly is just redraw the lines that we had up here, because that'll be helpful in determining our bounds. Right, so this is g of x, this is f of x, this was 1, this was -1, that was 2. Okay, so what do we want to do first? The bounds or the area? Let's do the bounds first. So we want we're summing up all of these square cross sections over here. So our left bound will be this line here, whatever x value is there, and our rightmost bound would be here, because we're taking all of these squares in between those 2 points, right? In between here and here. So this line here is along the y-axis, so this would be at x equals 0. That makes sense because we're bounded by the line x equals 0. And this rightmost point here, that's going to be equivalent to what we drew up here, so that will be at x equals 2. So our limits of integration will go from 0 to 2. Now, let's find the area. So a of x is a square, right? Our cross-sections are square. A of x represents the area of the cross-section. So it's going to be something like s squared, where s is the side length. But what is the side length? Let's go in here. For the first red square, the bigger one, this is our side length, right? It's in between the part of the base. And for the other cross-section, that's our side length, right? So they're definitely different sizes. It's not a constant. But actually, it's the distance between this line of our base and that line of our base, right? If I choose any point along this line, you can tell me what this side length will be simply by taking the difference of these 2 lines at x equals whatever that point is. So let's go back to this diagram. If we draw this line here, that's a side length of a square. So really, s is going to be equal to f of x minus g of x. And we'll square that, right? This is the distance between 2 curves. I think in the other video that I did, previous video about like area between 2 curves, we discussed this a little bit. But we're taking this minus this. That'll give us the distance between them. Okay, so we have equations for f of x and g of x. Let's plug them in. So this would be equal to 1 minus x over 2 minus negative 1 plus x over 2, and we're squaring that. So that's going to be equal to, oh boy, 2 minus x squared? Let me just make sure I'm not messing this up. Yes, that is correct. And now we can finally integrate. So volume will be equal to, our lower bound is 0, upper bound is 2. Our integrand is 2 minus x squared, that's a of x, and then we tack on a dx. And now it's just a simple definite integral. 0 to 2, 4 minus 4x plus x squared dx. That will be equal to 4x minus 2x squared plus 1/3 x cubed. Evaluated from 2 down to 0. Plug it in, and you'll get 8/3. So there you go. That is the volume of your shape. Pretty neat, but also a little bit tricky, right? Just gotta be okay with it. And so you might have noticed that this shape kind of looks like a pyramid. Oh, sorry, I don't know why I circled that. Like, it kind of looks like a pyramid, where this is like your square base, and then everything connects upwards to this one point. So maybe let's just test our hypothesis. The volume of a pyramid is equal to 1/3 area of the base times the height. In this case, the base is this square, or this square here. The side length would go from here to here, which in this above diagram is this, which is 2, so our side length is 2, so the area of the base is 4. 1/3 times 2 squared. And then the height, the height would be this. Note that it wouldn't be something from like the center of the square here, because of how this is a flat base and everything else is coming towards it. I'm going through this explanation really quickly because it doesn't matter too much. But this height is 2, so we multiply this by 2, and you get 8/3, so which is the same answer we got before. So just drawing a little parallel between the calculus version and the normal geometry version. Not every single shape will be something you're familiar with. Just for the purpose of this demonstration, I think this was a good choice. Okay, hopefully you got the hang of it. Let's do a couple more problems. So this problem, same exact curves. The only difference is now we have to do perpendicular to the y-axis. That's literally the only thing that changed. This letter went from x to y. Everything else is exactly the same. So what I'll do is I'll just like copy. I encourage you to memorize what this looks like. I'll bring it downwards, but just be familiar with it because I'll probably be referencing it a lot. Okay, so this is our base again, because we're using the same curves, but I'm going to get rid of this red dotted line because that might not be the cross section anymore. Okay, so let's try to redraw what's going on, and this should be a little bit quicker because we already know what the base looks like. So again, I'll do my skewed view. This is the x-axis, this is the y-axis, this is the z-axis, and then we have lines going like this and this. Okay, so now our cross sections are perpendicular to the y-axis. So again, we'll do a similar exercise to what we did before, where we draw like a line or like a plane that's perpendicular to the y-axis and work from there. So I'll draw like a line, something like this, and you can imagine that the plane goes upwards and extends this way, and the plane is perpendicular to the y-axis, as best as I could draw it, right? And again, we'll only be focusing at the part that's in between the curves that we're looking at. Let me just try to get back. So this is the only part that we're really curious about because that's the part that intersects our figure. At least we hope so, or it does, because that's what we're bounded by. So we'll do the same thing where we did before, where we try to build the square off of this side length and then draw the resulting figure. So the square can come upwards, and you want to make sure that it's like roughly the same side length. I'm not doing a great job of it, but you can see that kind of looks like a square. And then, like I said, I like to do the extremes. So I guess the next extreme would be this line here, because then we start to get smaller and smaller. So we can draw the red dotted line here, draw a square going off of this. Oh, I'm not good at this whatsoever. So that's another one, and then maybe one on the far side here. Something like this. And now we can start to draw lines to discern what the figure is. So maybe something like this, something like that, and then I think we need a couple more. We need one going up to here and one coming out here. And there we go. Something like this. It's really poorly drawn. I apologize, especially that line. Let me try to fix that. Something like that. I'll show you the better drawing behind the black square in just a moment, but hopefully you can visualize what's going on here. This is sort of the largest square, and then we're connecting to all corners of it, and then same thing is going on in the back here. So in a sense, it's kind of like two pyramids stacked on top of each other, but the main thing to note here is that the cross sections are still square. No matter where we slice it, we're still getting a square cross section. It's just a different figure now because we're doing it perpendicular to the y-axis. So with that in mind, let me get rid of this monstrosity. And let's take a look at hopefully a slightly better drawing. So here we go. Again, these are like the square cross sections that we drew before. This is another one. And then there's one in the far back here. And then what we did is, this is g of x, that's f of x. This is our line x equals 0. And then we sort of just connected the dots based off of the corners of the squares. And I gave the vertices or important points of this labels, just so that way I could shift the figure in a different way. So hopefully you can make the connection between these two figures, where this is point A, and then point F is up here. And this, oops, that's not a good drawing. This square right here corresponds to this cross section right here. And I guess this square right here would correspond to like a cross section down here. That's what the shape looks like. And as I was kind of saying, it's sort of like two pyramids stacked on top of each other. This is the base of the first pyramid, and it looks something like that. And then the bottom pyramid is here with the same base. So that's what the figure looks like. Now we have to find the volume. So we'll use the formula, integral from c to d of a of y times dy, because now our cross sections are perpendicular to the y-axis. So we have to use this different formula. How does that change things though? Well, first let's handle the limits of integration. So in the previous drawing, we started from x equals 0 and we ended at this x equals 2. Now we have to have that same perspective but from the y point of view. So we're going to start here and then build up these squares until we get to the large square, and then we come back down to this smaller square at the back. So we start here and end here. If we look at our base diagram here, this point A would be at -1 and F would be at +1. So D is going to be 1, C is going to be -1. Good. Now we have to figure out the A of y. So for that, let's resort to this. In the previous problem, we drew our cross sections like this, and we're like, okay, that's the side length. That gives us the area, s squared. We'll do a very similar thing here. Except now, the lines go like this. So this would be s. And in this case, you're like, okay, that's actually not that bad at all, because I know that this is the line x equals 0. So the distance here is just whatever the x value is here, determined by this g of x line. Which is all good until we go up here. Now, s depends on f of x instead of g of x, right? So it's going to switch its dependencies once we cross this line. So when we have this switch of dependencies, it means we're going to have to do a change, or we're going to have to split apart the integral, and this occurs at 0. So let's sort of write out what I'm saying. So from -1, like when y is in between -1 and 0, the value for s that's going to be bounded by these two lines here, this one and g of x, by x equals 0 and g of x. So s is going to be equal to g of x minus 0, which in this case is -1 plus x over 2, which is fine, except remember that we're going to eventually be doing s squared, right? To get the area of the cross section, we're going to have to square it. But the area should be a function of y. So we have to change this to be in terms of y. So if we start with y equals negative 1 plus x over 2, we're going to solve for x in terms of y. So this would tell us that x is equal to 2y plus 2. And now we have to consider the other part, when y is in between 0 and 1. From 0 in between y1, the value for s is bounded by, now it's bounded it's bounded by this line x equals 0 again, but now it's f of x instead of g of x. X equals 0 and f of x. So s is going to be equal to f of x minus 0, which is 1 minus x over 2. And again, we'll do the same thing. Y equals 1 minus x over 2. Solve for x in terms of y. 2 minus 2y. Now we're ready to solve the integral. So the volume, we said, is going to be equal to, we said the lower bound was negative 1, upper bound was 1, a of y dy, but we know a of y is going to be different depending on what the value of y is. So we'll break it apart into from negative 1 to 0 of something plus 0 to 1 of something. What are these somethings? Well, we have the side lengths in terms of y, right? This is the side length for the first one, so we're going to square that, right? The area in terms of y at some point in between y equals negative 1 and 0 is going to be equal to the side length, 2y plus 2, squared. And same thing for the other part, 2 minus 2y squared. And now we just have to solve this integral. So this will be integral from negative 1 to 0 of 4y squared plus 8y plus 4 dy plus the integral from 0 to 1 of 4y squared minus 8y plus 4 dy. And hopefully you remember your integration rules, power rule, things like that, and the fundamental theorem of calculus to evaluate these. I won't bore you with plugging in the values and stuff. I'll trust that you can do that on your own. Just use your fundamental theorem of calculus. But you should get the value 8/3, which is quite curious because that's the volume we got in the first problem, but it was a completely different shape. So if you want, you can test this out using geometry again. Let me try to think really quickly. Ooh, it's actually not super easy to do in my head. Actually, no, it's not too bad. 2, 4, 4, 1. Yeah, it's basically the same thing. Just do 2 square-base pyramids, and you'll get the same answer, 8/3. So, yeah, similar to the first problem, but the main difference is what we spent the most time on is how to take the cross-sections, this time perpendicular to the y-axis. Hopefully this is starting to make sense. Again, I apologize for my drawings, but I really think that hopefully take a look at these two drawings and try to draw the correlation between them. One more problem, and then we'll call it a day. Same exact lines, f of x, g of x, x equals 0. Same exact things. Now our cross-sections are different. We're using semicircle cross-sections perpendicular to the x-axis. Okay, so let me copy this. Nope. And we're going to bring this down here. And I'm going to have to erase some of this. So now again, we're similar to the first problem. We're going to be looking at the x-axis this time. Our cross-sections will be perpendicular to that axis. I just need to clean this up a little bit and we should be good to go. So same base, except now our cross-sections will be something like that. But we'll come back to that in just a moment. Let's draw the figure again. So we got our y-axis here. We got our x-axis here. We got our z-axis here. And I'll just label these. And again, we'll draw our base. Hopefully you're getting comfortable with what this base looks like. This is 2, this is -1, this is 1. And again, we'll do the same thing where you pretend there's a plane slicing through it perpendicular to the x-axis, but as we've shown in the previous two problems, the only part that really matters is what goes within our figure. So in this case, it'll be something like this line here. Before we were looking at square cross sections. So we just took that line and kind of put it upwards and drew a square. Now we have to draw a semicircle. So we have like a semicircle looks like this. That's a pretty bad semicircle. But this line here correlates to this dotted line. So we have to draw this curved line that goes around it. Whoops, that is not good. And the curve, it's not necessarily just arbitrary. Remember, it's a semicircle. So the radius has to be the same no matter where we are in the circle, right? We can't just extend it super high upwards. But that's one cross section. Let's do another cross section and then we'll look at the extreme. So something like this. And then do our best to draw a semicircle. I am not very good at this, but hopefully you're starting to see something, maybe not, just because of how bad I'm drawing it. Now let's look at the extreme, which would be along this axis here. And it'll look something like this. I'm doing my best here. And now we can start to draw lines to describe the figure, except it's a little bit harder now because with the squares we had the corners to go along. Here it's a curved surface, so we can draw these lines which will hopefully indicate curvature. But really these furthest blue lines are what's really describing the figure. Something like that. And again, you should test it. If you slice down on this, on the x-axis, perpendicular to the x-axis, are you going to get these semicircle cross-sections? And in this case, maybe you're a little reluctant because I drew it so poorly, but the answer is yes. So let's take a look at my other drawing, and man, hopefully, I really hope that's clearer. Okay, it's not much clearer, but yeah, the thick blue lines describe the farthest point of the figure. That's what it's bounded on. This dotted blue line in the back it's like an edge of the figure, and then we can see that it's curved. It's a curved surface. These aren't edges. It's just showing the length of it. Maybe you can kind of tell what this shape looks like, but we'll keep that a secret for the moment. Let's try to solve this problem. I told you I'm not an artist. I'm trying my best though. Alright, so what's the volume going to be? That's going to be integral from a to b of a of x dx, because again, the cross sections are perpendicular to the x-axis, so we have to use this a of x formula this time. Okay, so the bounds of integration are going to be the same as the first problem because it's the same curves. So it's going to be equal to the integral from 0 to 2 of a of x dx. But now what's the area going to be? It's not s squared anymore. We're working with a semicircle, so it's pi r squared. Pi r squared dx. And it's not really great to have this r and the x in there, but for the moment being, just let it go, okay? What is r? Well, let's take a look here. This is the part of the cross-section that we drew. With square cross-sections, this was s, right? But you'll remember when I was drawing this semicircle here, I said it can't just be an arbitrary curved thing. You have to make sure that the radius is the same along all of the points, the radius r. And notice that the radius depends on the center point of that semicircle, meaning the center of like the diameter part, right here. So this would be an R, this would be an R, this would be an R. So equivalently, in this diagram, that would be an R, right? So this right here is R. But wait a second, we said that when we did squares, this full thing was S. So R is going to be 1/2 of S. That kind of makes sense, right? Because this is like the diameter. S is sort of like the diameter and we want half of it. Great, so we found S by doing f of x minus g of x. We just have to take half of that, right? So let's just do an aside here. R is going to be 1/2 f of x minus g of x. If we remember from before, f of x minus g of x was 2 minus 2y. Okay, I don't remember. I have to double check now. Oh, sorry, it was 2 minus x. All right, I'm not on my game today. Yeah, of course it wouldn't be y. Okay, and this would be 1 minus x over 2. That's our radius. Now we can substitute it back in, and we'll see that the x will be replaced with the r, and everything will be compatible. So this is going to be equal to 0 to 2 pi. The radius we just said is 1 minus x over 2 squared dx. And let's evaluate this. Do a couple steps at once. Bring out the pi and expand the inside. X squared over 4 minus 2 times x over 2 would just be an x plus 1 dx. This will be pi times x cubed over 12 minus x squared over 2 plus x, evaluated from 2 down to 0. That's going to be pi times 8 over 12 minus 2 plus 2, which is going to be equal to 2 pi over 3. And I hope that is the correct answer. No, it's not. What did I do wrong? What did I do wrong? Oh, I know what I did wrong. Semicircle cross sections, not circle cross sections. So this should be a pi over 2. Let me actually change the color so it's highlighted. Right? Got to be very careful with these cross sections. So this will be just pi over 3 as our answer. Right? Be careful when you're doing these cross sections, make sure that you have the correct formula. I didn't, and I made that silly mistake. Anyways, we got our answer, pi over 3. I made a little comment before that maybe you're able to tell what this figure actually looks like. So maybe you deduce that, hey, that kind of looks like half of a cone. If I do something like this, can't draw well. Something like that, and sort of draw the rest of it. You're like, hey, that kind of looks like a cone. And you'd be right, we can find the volume of this. So the volume of a cone is equal to 1/3 pi r squared h. We're looking for half the volume of the cone, so we take half of it. So 1/2 times 1/3 pi r squared h. R in this case would be one of these red lines. We said that this is -1, that's 1, so we can just say r is equal to 1 times pi times 1 squared. H is going to be this, from the point to the center of the circle, and we said that this is 2, so h will be 2. You can evaluate this out, you get 2 pi over 6 equals pi over 3. Like I said before, not all of these problems will have these simple geometric shapes or relatively simple. I just chose these for the purpose of demonstration that you can verify your answer using geometry, but you solve them using calculus. Hopefully this lesson made sense, and hopefully you're now able to find these more complex volumes. I highly encourage, if you're a visual learner like me, to take the time to draw out these figures. It can be difficult, but I think once you start to draw them out, and once you understand the formula, what's going on here, it'll all make sense. think about what I said earlier about how finding volumes is basically the same thing as taking a bunch of papers of different sizes and stacking them on top of each other to create a three-dimensional figure. For example, like, imagine this is a piece of paper, and then you do it like a slightly smaller piece of paper on top of that, and then a slightly smaller one on top of that, and this pile is going to grow in thickness, and eventually you'll get like a pyramid shape in this case. And if you find the volumes of each of those tiny pieces of paper and add them up, you'll get the volume of the large figure. That's what we're doing here. The cross sections are the papers, and we're finding the volumes of those papers by using this